Welcome to the 8.5 video on factoring trinomials in the form 1x squared plus or minus bx plus or minus c. Our objective, I can factor trinomials in this form. So it's a standard form trinomial, specifically when x squared has a coefficient of 1. What is our key concept when we're factoring these trinomials? How can you effectively factor a trinomial when a is 1, and how do you effectively factor a trinomial when a is not equal to 1, but there is a greatest common factor. The first question we'll answer today. The next one will be in the next video. So you can write some trinomials in the form x squared plus or minus bx plus or minus c as the product of two binomials. Now you notice the word sum here is highlighted because this is not possible for all trinomials. There are simply some trinomials that aren't factorable. It is impossible to write them in factored form. To understand how this process of determining which ones could even be factored, let's look at an example. X plus 3 times x plus 7. If you were to distribute out the x and the 3 to the x plus the 7, x times x is x squared, and you would get x times 7 is 7x, and 3 times x is 3x, and so you see that as that orange 7 plus 3 times x. It's just, we're showing that there's 7 copies and 3 copies, and then the 3 gets distributed to 7, which we see in blue, and then when you combine your like terms, you get x squared plus 10x plus 21. So what's the pattern here? The coefficient of the x squared term is 1. And that's because when we do x times x, we're always going to have just a single x times a single x. Coefficient's always going to be 1. The coefficient for the x term, the middle term in orange, is the sum of the constants in the binomial. So for example, if you look back to the original binomial, 3 and 7 are the constants. 3 plus 7 is 10, which is why we have 10x. And the trinomial's constant, in this case the 21, is the product or the multiplication of the constants in the binomial. So again, the constants were 3 and 7. 3 times 7 is 21. That's because we're going to multiply 3 and 7. If you think about the FOIL, that's the L in FOIL. So what are you looking for? So like that's a great example when you see everything worked out, but what if you don't know what's happening? When you factor something, you are looking for two numbers that will multiply to the c, the constant, and will add to the b value. Those two values that simultaneously multiply to c and add to b will be the constants in the binomial multiplication problem. So for example, x squared plus 2x minus 8. Your b value is 2, so we're looking for two numbers that add to 2, and your c value is negative 8, and so you're looking for two numbers that multiply to negative 8. Two numbers that multiply to negative 8 and add to 2 are positive 4 and negative 2. So the factored form of x squared plus 2x minus 8 is x plus 4 times x minus 2. And if I were to redistribute, so multiply the x by the negative 2, the 4 by the x, and the 4 by the negative 2, I'd get back to that x squared plus 2x minus 8. Why does this work? Well, when you change the dimensions of a rectangle, you're changing the perimeter while keeping the area constant, assuming you're keeping the area constant. So the area model is a great analogy for this. When you factor a trinomial, you are looking for the dimensions of a rectangle that has the area of the original trinomial. So for the example on the left, the dimensions are 2x plus 2 on the left and 3x plus 1 on the right. If I am trying to find the factored form of the original trinomial, so in this case the area or the sum of all the pieces, so that's 6x squared plus 8x plus 2, the dimensions of a rectangle around that, and I can orient it however I want, will be the factored form. There is only one possible length-width combination for a given rectangle with a set perimeter and area combination. So if I put these constraints on the rectangle, the area model, and say it has to have this perimeter, it has to have this area, there is only one combination in the whole universe that will make that true. If that example even works, it might be that the components of an area model are not able to be arranged in a rectangle. That, like this example, maybe if there were one more x piece, wouldn't be able to fit into an orientation of a rectangle. And that's why not all trinomials are factorable. So let's do some factoring and let's look for some patterns. Let's factor x squared plus 8x plus 15. So we're looking for two numbers that add to b, so in this case 8, multiply to c, which is 15. When looking for that list of numbers, it's always better to start with the list of numbers that multiply, because the list of numbers that add to any given number, so in this case 8, is infinitely long. You can do 1 plus 7, 2 plus 6, so on, but I could also do 8 plus 0, 9 plus negative 1. You can do decimals, you can do fractions. The list of numbers that add to any given number is infinitely long. And while the list of numbers that multiply to any given number, in this case c, could be long, it is finite. It has a start and it has a stop point. So listing the numbers that multiply is a much more effective method. So what numbers multiply to 15? Well, 1 times 15, 3 times 5, and that's it, right? I could use the commutative property and do 5 times 3, but that's all the combos. So what combination could I do? Well, I could do x plus 3 times x plus 5. So 3 plus 5 is 8, 3 times 5 is 15. Let's try another one. X squared plus 11x plus 24. Your b value is 11, so we're looking for two numbers that add to 11, and multiply to 24, which is our c. The factors of 24 are 1 and 24, 2 and 12, 3 and 8, and 4 and 6. If you list it out in pairs like this, you know you've exhausted your list, because if you'll notice, 4 and 6 are at the bottom, and there's only one number in between them. So if I know I check 5 doesn't go into 24. The next one that I could list would be 6 times 4, but I already have 6 on the other side. It's almost like a snake. I go down the left side and then up the right side, and that's all the factors. So you can cut your time in half if you list them like this. So from this list, what adds to 11 and multiplies to 24? Well, 8 and 3. 8 times 3 is 24. 8 plus 3 is 11. And so when you'll notice that at the top, it says b is greater than 0, c is greater than 0. When b and c are both positive, you'll end up with x plus something times x plus something. It's the template. So when b and c are both greater than 0, you'll have double pluses in your factored form. Well, what happens if b is less than 0 and c is greater than 0? So in other words, b is a negative and c is positive. So an example of this would be x squared minus 11x plus 24, or x squared minus 6x plus 8. And so let's do the exact same thing, exact same protocol. What numbers add to b, negative 11, multiply to c, 24? List out the factors of 24. 1, 24, 2 and 12, 3 and 8, 4 and 6. We have them all. And then what combination, positive or negative, could get us to negative 11? Now we know that we have negative 11, so the fact that negative 11 or 11 isn't in our list of factors tells us that we're going to have some combination, and we're going to need to use our integer rules. Well, negative 3 and negative 8 give us 11. So why does this work? Well, when I multiply the negative 3 by the negative 8, if I were to redistribute, negative 3 times negative 8 is positive 24. And so you might see the pattern here. When b is less than 0 and c is greater than 0, or when b is negative, c is positive, you'll end up with double negatives, just like on the previous slide we ended up with double positives. And this is because when you add negatives, it stays negative, so b will continue to be negative. But when you multiply negatives, so when you multiply to get c, a negative times a negative is positive. So for x squared minus 6x plus 8, we're looking for two numbers that add to negative 6, multiplies to positive 8. Factors of 8 are 1 and 8, 2 and 4. And so what combination could you have? Well, negative 4 and negative 2 are the only combinations from that list that will get us to negative 6, because negative 4 plus negative 2 is negative 6, but negative 4 times negative 2 is positive 8. The last example is what happens when c is less than 0, because the first two, c was bigger than 0 in both cases, and now what happens if c is less than 0? So you can see these examples, sometimes b is positive, sometimes b is negative. But what happens when c is less than 0? So let's start with the first one. Same protocol again. Add to b, multiply to c. So add to 2, multiply to negative 15. Let's list out the factors of positive 15 and then see what happens. So we got 1 and 15, 3 and 5. That's it. So how are you going to get negative 15? Well, the only way to get a negative number out of a multiplication problem is one of them has to be positive and one of them has to be negative, because if you multiply two negatives, you're going to get a positive. So if I do that, if I know one of them has to be negative, exactly one of them has to be negative, the combination has to be positive 5 and negative 2. And I know that it has to be positive 5 versus negative 5 because I need to get that positive 2 for b. So if b is positive but c is negative, b being positive will force the bigger of the two factors to have the plus sign and the smaller of the two factors to have the negative sign. We'll see the opposite of this in the next example. If we're looking for two numbers that add to -4 and multiply to -21, list your factors of 21. 1 and 21, 3 and 7, and that's it. And so what combination could you have knowing that one's going to be positive and one's going to be negative? Well, 7 and 3 have a relationship that's tied to 4. So the question is it +7 and -3 or -3 and +7? Well, the fact that b is -4 tells us that we have more negativity, and so it's going to have to be -7. X -7, x plus 4. Last one, we got b is +9, c is -36. So we're looking for two numbers that add to 9, multiply -36. The fact that b is positive tells me that I'm going to have a plus bigger number and then a minus something else in the back. So numbers that multiply to 36, we got 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. We have quite a long list of numbers to choose from. So which ones give us 9 in some positive, negative relationship? We have a 4 and a 9, but 9 is one of the numbers, and so that's not going to help us with adding. 3 and 12 have a relationship with 9. 12 minus 3 is 9, so the fact that b is +9 tells me x plus 12, x minus 3, because 12 minus 3, we're going to have 12x minus 3x will give us 9x, but 12 times -3 is -36.